we'll chill for a few more minutes and then get started while I get in the zone. So probably 33A is the most useful lower division math. Yeah, that's probably pretty accurate. Probably 33A, maybe 32A. You know, I mean, it depends what you do, but in general, I think all things being equal, typically I would call 32B the hardest lower division course, but all things aren't ever equal, and it, you know, you guys know it really depends on the professor and depends on a lot of things. Okay. Yeah, in an ideal world, they would require 33A before taking 32A and 32B. Mathematically, that makes the most sense. For whatever reason, though, that's not usually standard. Yeah, so I guess I can, maybe let me start out by giving you the definitive. I've given this to some other people, but this will get us kicked off, and then we can do some math. These are definitive 30 series power rankings for math classes. In my opinion, which is the correct opinion. Take notes because this is probably the most important thing you'll learn tonight. At the bottom is 31A. It's super boring. Not a whole lot to say there. Next in line is 33B. Interesting stuff, but I think the execution of a typical 33B class at UCLA is kind of blah. It could be more interesting. Then let's go with 32A. 32A is kind of similar to 31A to me in the sense that in general, differential calculus isn't super thrilling. I like the integration aspect more. And then 33A. Linear algebra is amazing, especially like 115 level linear algebra. But 33A, there's a lot of computation, and I'm not so big on that. I don't know what math 42 is, but I'll throw 61 in here also. I need to think about that though. Honestly, I'd probably put 61 here. I guess I can erase. It's a pretty close call for last between 61 and 31A, I think. Okay, so then in second place is 32B. And then 31B is clearly best. So I have a feeling many of you do not agree with that. But 31B is by far my favorite class. And it's a shame because I think again, I'm going on pure subject material. And, you know, depending on what kind of professors you have, it depends. But this is my controversial take. Okay. Proof. Now, let's do some math. I guess I'll share the results that I'm eating both Triscuits and yogurt later. So that's exciting. Triscuits are crackers. Do you guys not know what Triscuits are? They're just, yeah, they're kinds of crackers. They're pretty good. Okay, so as usual, the game plan for tonight is I have a fair number of examples that are intended to be on the more interesting and difficult side, not because I think that's what you should necessarily expect to be on an exam. But mostly because I want to be able to talk about a lot of these new concepts that we've learned and lead you through some more interesting questions to get some practice kind of synthesizing a lot of the techniques that we've learned in class. Sound good? So as usual, if you have any questions, you can always let me know. I want to focus on examples that I came up with just for the sake of having new things to think about. But then, you know, if you have questions about practice finals or something, if I'm not too tired, we can talk about that. And then obviously tomorrow we'll have some more time as well. So got a private question, which was at some point, can I tell you guys what we have to prove, show before using each theorem? Yeah, I'll make a comment about that at some point. The short, not helpful answer is in general not a lot, and I think people tend to overthink that kind of thing. But I'll make a comment about that at some point. Yeah. Okay, ready? I don't know what I want to start off with. Let me think for a sec. Let's start off with this first one I wrote. Okay, the first one. Okay, Katie just wrote this one down, so that means we have to do it. Same with Elijah. So I'll read it out loud and I'll let you guys think. And I want ideas, I want thoughts, suggestions, feelings. I want it all. So we have a curve. It's an oriented curve. And I guess this is sort of poorly written. These are all supposed to be straight line segments. Now that I'm reading this again, I should have specified that. So maybe straight lines from different points. So 0, 0, 0 to 1, 1, 1 to 0, 2, 3 to negative 1, 1, 2. And then back to 0, 0. So, and I think this is what Ricardo's getting at maybe, is that, you know, maybe visualizing exactly what this looks like is a little weird, but it's made up of 4 straight line segments, which means since we start and end at the same place, this is a closed loop. So not to put words in Ricardo's mouth or into his Zoom chat, but probably what he's thinking by checking the curl is, well, I don't know. I would say, you know, maybe if we check the curl and ultimately could show that the vector field's conservative, then we wouldn't have a whole lot of work to do, right? And it would be 0. So maybe conservative. let's check. Well, let me compute the curl and then I'll comment on the actual conservative stuff, but let's compute the curl. Why not? So the curl of f is going to be the cross product of this derivative vector with the vector field. So negative yx, x squared, and e to the z cubed. Okay, so as always, do it however you want. Boom, boom is going to be 0 minus 0, I think. And then the second component will be 0 minus 0. Exciting, we're close. Uh-oh, but unfortunately, 2x minus negative x is 3x. Okay, so the curl isn't 0, which means, you know, just since I guess we're in a review session, to think about what this means. You don't necessarily need to write this down in a solution if it doesn't matter, but since the curl is not 0, this definitely tells us that the vector field is not conservative. So all that means is that we can't immediately say it's 0. And unfortunately, we have some more work to do. But it's a good thought. Other thoughts? Okay, so I'm gonna, and you know, maybe, okay, so I think you have some good ideas. Maybe let me say one thing first, and then I'll comment on some of the ideas. Two planes. The first thing that I was going to say is one thing that you can always do, right, is do it directly. Like this is a line integral. We could just parameterize the curve and evaluate things directly. So that's the worst y I've ever drawn in my life. Right, but one reason why I don't want to do that is what Elijah's pointing out, and that's that there would be 4 different segments to do, and that's annoying. We've got better things to do than parameterize 4 different times. Okay, true. So you do have 72 hours. So if you need to parameterize 4 different curves, go for it. But there's another reason why I'm not too thrilled about that idea. And yeah, so I like the Stokes Theorem idea. I'll get to that in a second. But before I do that, what's the other reason I really don't like the idea of doing it directly, aside from there being 4 components to the curve? Question is, like, do you think we could even do it? Yeah, exactly. This thing right here, if we do this directly, we're going to have to deal with it. And integrating that is hard, probably. But since Ricardo suggested that we compute the curl, I know that if we, for example, do something with Stokes' theorem, where we instead integrate the curl over some surface, all that nasty stuff went away and it might not be so bad. Okay. So no 4 sides, or 4 curves maybe, and this e to the z cubed thing. Yeah, so earlier, I think when you suggested Green's theorem, technically, you know, they're all the same at the end of the day, but technically, since Green's theorem is a statement about 2-dimensional things, and this is a curve in 3 dimensions, rather than Green's, we want to think about Stokes' theorem, which you can think about as being kind of the 3-dimensional version of Green's theorem. So it sounds like what you guys are telling me, and I'm going to scroll down, but I can scroll back up. I'll need to remind myself what the points are. Is that, well, maybe let me remind you what Stokes Theorem says before we talk about using it. Stokes Theorem says that if you have a surface, I won't write all the words, I'll just write down the equation. It says that if you have a surface, the surface integral of the curl over that surface gives you the line integral over the boundary curve of the vector field. So when I think about using Stokes Theorem, I look at the thing I want. That looks like this. So maybe when we use Stokes Theorem, we could instead go this way and compute this, and that might be easier. Seems like it might be because, like, you know, I pointed out earlier, the curl is a lot simpler without this e to the z cubed thing. So this is what we want to do, but the first thing that we have to do, and this is surprisingly, not surprisingly, but it might be a little more subtle than you think, is right now, if you look at the statement of the problem, is there a surface anywhere? No. So if we want to use Stokes Theorem, we definitely can, but we're going to have to come up with a surface. Even more than, we don't even have a surface yet, right? So we have to pick like literally a surface whose boundary is this curve. That's our first order of business. Okay, so okay, so really quickly, I got a private question. Where will I be posting the recording? On YouTube, on the YouTube channel. Hope probably by the end of tonight or maybe by tomorrow morning. Yeah. Okay, so Ricardo and Elijah have good ideas, which is maybe there's a plane containing these 4 points. And my question would be, how do you know? How do you know it's a plane? Because, think about this. If I just draw 4 random points, could we make 2 lines and cross them? Maybe. But all I was saying is, like, in general, if I were to draw 4 points in space, do those 4 points lie on a plane? Not necessarily, right? I mean, they could, and they do in this case, but that'll be something that we probably have to show. In general, if you draw 4 points sitting in space, they're probably not going to lie on a plane. So the first thing that we have to do here is kind of justify that if we want to make some kind of plane containing these. So straight lines in C is a closed loop. I mean, so let me put it this way. What if I changed this number to be 4, but still straight lines and still a closed loop? These 4 points no longer lie on a plane. So it's going to be a little more subtle than that. Okay, so I got a private suggestion, which is, I think, thinking about the right thing, which is, could we say that there are only 2 non-parallel vectors between these points? Yeah, that's getting to the idea. Let me show you what I would do. So I keep forgetting what these points are. So let me zoom out really quick. So one of the points is 0, 0, 0. One of the points is 1, 1, 1. This is going to be not the greatest drawing, so I apologize in advance. So there's my 1, 1, 1. 0, 2, 3 would be like up here. And then negative 1, 1, 2 would be like here, sort of. So there's C. The way I would determine if these were on a plane is I would take I think it is. Better be. I've been drawing the same 3 axes for my entire life, so I think it's a right-handed system. Anyway, so if I were to take this vector plus this vector, what if we get this point? Then they lie on a plane. That's really all we have to do. So this vector right here, maybe let me write this out. So note that, and I think that's the case. So what would those 2 vectors be? It would be like this plus this. This was like the farthest away tippy top corner, right? So if you take this point plus this point, what do you get? You get exactly that point. So isn't that pretty unique to different cases? I don't know what that means. No, so if you moved, maybe let me say it this way. The plane generated by these 2 vectors, and all you linear algebra people could tell me what I'm about to say next, but the plane generated by these 2 vectors is all the possible linear combinations of those 2 vectors. So every point on the plane containing those 2 things is going to have to be some algebraic sum. And so if you moved it up a little bit, it would, yeah, it couldn't work that way. So really all we have to say is that 1, 1, 1 plus negative 1, 1, 2, this is 0, 2, 3. So this means all 4 points lie on a plane. Okay, cool. So let me let S be the part of the plane containing these 4 points, which, we don't really know what that is yet, but there's some plane. So let S be that plane containing these points, which is contained in the curve C, which is enclosed by C. That could be our surface, and that's what we could apply Stokes Theorem to. So let me color that in. Whoa, that was a big boy. There's S. Okay, and actually, there's something that I'm missing, which is I need to give S an orientation, right? Anytime we talk about Stokes Theorem, since this is a vector surface integral, this is an oriented surface. And we can do whatever we want. So, this is a plane. Because it's not a vertical plane, I could specify an orientation by saying, well, this is either going to be oriented up or oriented down. Ricardo says up, so that's what we'll do. But you could do whatever you want, doesn't really matter. So I'll say orient S upwards. Okay, so far so good. We are locked and loaded and ready to apply Stokes Theorem. We'll have some work to do after that, but we can at least apply the theorem. So by Stokes Theorem, Actually, maybe let me say one more thing. Okay, so yeah, this is a good question. Does the orientation of the surface have to match with the orientation of the curve? Not necessarily, but you have to take that into account. So that's going to be the next thing I say, is that here's my next question. What is the boundary of S? I'll zoom in. It's C, exactly. So if I think about, and again, I'm asking about the orientation here. So the question is it C or is it negative C? And you guys are right, it is C. Right, so if we decided to point it downwards, the boundary of S would be negative C, and that's fine. We could still use Stokes Theorem. We would just pick up a negative sign, exactly. But here I stick my thumb up, and then I curl my right hand fingers, and that curling motion goes like this, and that matches the movement of the curve nearby. So the boundary of S is in fact C. Okay, so now by Stokes Theorem, the integral of f along C, which is ultimately the thing that we care about, is the surface integral over S of the curl of f. And thankfully, we already computed the curl, so I don't have to do that again. The curl is 0, 0, 3x dot ds. And now, all we have to do is evaluate a surface integral. Okay? So I'm actually gonna, I'm gonna talk about this analogy that Noah used in class last week or whenever, because this is gonna be a decently involved problem. And I wanna make sure that it's organized correctly in your head. So what we just did is we started out with a line integral. And we applied Stokes Theorem and all that does, we're completely done with Stokes Theorem now. Don't have to care about it at all. Stokes Theorem is a bridge from the world of line integrals to the world of surface integrals. So now we started here and we walked over here. We're in the world of vector surface integrals, and all we have to do now is just evaluate the surface integral. That's it. Doesn't matter where it came from, doesn't matter what this means. We just need to do whatever we need to do to evaluate the surface integral. So, next question, how do we do that? Every one of you knows the next word. Yes, we need to parameterize the plane. Okay. Okay, so I got a private question, which was, can I explain again how we knew it was C and not negative C? Yeah, so the first thing I'll say is that we decided to orient the surface upwards completely arbitrarily. Maybe Ricardo saw in advance that it would work out this way, but you don't have to. If you wanted to, you could orient the surface downwards. That's totally fine. So the upward orientation of the surface was just our choice. And we could have made the other choice. We just happened to make the upwards choice. So now, this argument really relied on my picture, which is not the greatest. But in my picture, let me write these 3 points here because I'll use them again. I forget. 0, 2, 3. And negative 1, 1, 2. So when I drew my shitty picture, it's not the greatest picture, but it is important because it does indicate the direction of the curve. It might be kind of hard to tell, but if you think about the placement of all of these points in 3 dimensions, like this point is going to be in the positive x direction. This other corner is going to be in the negative x direction. So the curve is going, another way to say this is if you looked from above, if you grew wings and flew up here and looked down, it would look like the curve was going counterclockwise from that viewpoint. So when we figured out the boundary orientation, one way to do this is to stick your thumb in the direction of whatever normal vector you pick, of your right hand specifically. So stick your right thumb in the direction of the purple vector and curl your fingers. And my purple arrow here isn't very good, but when you curl your fingers in that direction, they're going to curl like that. And then that curling motion tells you the direction of the boundary curve. So what that means is that the boundary curve is going this direction, and that happens to be the same direction as C. So that was why the boundary of S is C rather than like negative C, if that helped. Okay. Now, the next slightly interesting thing about this question is we need to parameterize the plane. But right now, we don't actually have the equation for the plane, right? So one way that we could approach this is to find the equation of the plane. But we could actually, we could do something a little, no, we don't. We could do, what I was going to say is that if it were me, I wouldn't even find the equation of the plane. I would just write down a faster parameterization. I don't know if any of you guys know what that would be. Wait. Okay, so Ricardo has a good point, which is, I see what you're saying. We just care about the normal vector. I don't disagree, but the problem is that you have to be a little careful because your parameterization, you could parameterize the same surface differently and get different normal vectors, right? So I think in this one you could get away with just using the normal vector, but in general you do need to be careful because of the resulting bounds. But that's a good point. Yeah. But just to practice getting some parameterizations in anyway. Yes, so I think Dara has the correct idea, which is what I was going to write here is, let me go back to my picture. This vector is 1, 1, 1. This vector is negative 1, 1, 2. So I can take u times one of them and v times the other and restrict u from 0 and 1. And that will be a parameterization of the plane. Yes, we are, most of 32A and 32B is, at least in my head, is doing linear algebra. without actually saying it, which is why they should really require it beforehand. But let me move on, and I might make some more comments about this because there are various ways that you can go about this problem. So I need to add a new page. But I want to make sure that this parameterization is okay with everyone. If you think about taking this vector and scaling it by all possible multiples between 0 and 1, and then the other side and scaling it with all multiples of 0 and 1, and then you allow to add those together, at the end of the day, you're going to trace out the parallelogram defined by those things. And that would be a parameterization. You could parameterize in other ways. Yeah, so I got a private question, which was, can I explain the U and V bounds? You could think about this in terms of the edges. So if I zoom into my picture here, this vector is U. And so what I'm saying is that I'm allowed to take this vector and stretch it by any number smaller than 1 to get all the points like on this edge. And I don't, like, I wouldn't be allowed to multiply it by 2 because that would put me like over here. And that point isn't on the little parallelogram. Yeah, so this is a parallelogram. That's correct. Oh, should we check that? We kind of did actually with our first statement. This effectively, this shows that we're on a plane, and it also shows that this is a parallelogram. So yeah, that's a good question. So I don't want to stretch this vector more than 1 because that would put me over here, but I also don't want to stretch it by any negative numbers because that would put me back here. So the only thing I'm allowed to stretch this vector by is numbers between 0 and 1 to trace out this edge. Likewise, the same thing with this edge. I don't want to send V, or I don't want to multiply this vector by something bigger than 1 because it'll put me out there. That helps. Any other questions about the parameterization? So can we use this method of parameterization for any plane? Yes. Well, if your region is a parallelogram in a plane, then yes. That's correct. Let me verbally say out loud that you could do other things as well. For example, you could just find the equation of that plane, like find the Euclidean equation of the plane. It'd be like ax plus by plus cz equals something, right? And then once you have the equation, you could find a parameterization by doing something like calling x and y the parameters and then going from there. That would totally work if that makes more sense to you. If you do that, you'll have to do a change of variables, which could be fun as well. But this also works. Okay, so let's move on. So that's a parameterization, but we need to make sure that the orientation is correct, right? So we need to check that G of UV is oriented upwards. I can see geometrically that it's going to be because I'm going to take by the right-hand rule the right edge cross the left edge, and that's going to give me an upward pointing vector, but we should verify that computationally. So how do we do that? The normal vector here. And again, to review this process, when you write down a surface parameterization, and you write down the variables in the order, UV in this case, but you pick whatever order you want, your normal vector, you have to cross the derivatives in that order. that's how we define the orientation of a parameterization. So what this means is that the normal vector for this parameterization is the u derivative cross the v derivative in that order. Well, the u derivative, unsurprisingly, is 1, 1, 1. The v derivative is negative 1, 1, 2. And so what's the normal vector? 2 minus 1 is 1. Negative 1 minus 2 is negative 3. And 1 minus negative 1 is 2. I think. And the question is this oriented upwards? The answer is yes, because the z coordinate here is positive. So the z component is positive, so points upwards, so oriented correctly. And if that's okay so far, then what we're allowed to do now is take the surface integral and use our parameterization to turn it into a double integral. So then the surface integral over this surface of whatever our thing was 0, 0, 3x. How do we use the parameterization to turn this into a double integral? Let me do this actually. Let me call this region. Let me call this E. So we get a double integral over E of something, and yeah, so Dara is helping me out here. Dot the normal vector, I'll come back to that in a second, dA of UV. Now, what Dara's pointed out is that when we use the parameterization to convert this into a double integral, we need to figure out how to rewrite 3x in terms of our vector, or in terms of our parameterization. So I think what is happening is if I squish these things together, right? This would be u minus v, u plus v, and u plus 2v. That would be an equivalent way to write our parameterization. This is x, right? That's the x component. So 3 times x is exactly going to be 3 times u minus v. That's our parameterization step. And in the picture up here, what we've now done is we've walked across another bridge, which is parameterization. That puts us in the world of double integrals. And again, now we just have a double, well, let me write it out maybe. The dot product's pretty easy. I guess we'll get 6 u minus v dA of uv. And now we just have a double integral to evaluate, and we're back in week 1 of the class, right? So what do? We take the double integral, turn it into an iterated integral, which is extremely easy in this case. Like in general, it might be more complicated. but this is kind of the structure of what we're doing. So I got a private question, which was, why did I dot it with the normal vector? So maybe let me write this down in general. Anytime you have a vector surface integral, how do you actually evaluate it? Or in other words, what does this notation mean? Once you have a parameterization, you use your parameterization to rewrite the vector field, and then you dot with the normal vector, and then you get a UV region to do a double integral over. So the reason why I dotted with the normal vector is because that's exactly how we evaluate vector surface integrals in general. This is exactly the process by which you evaluate one of these things. You compute the normal vector and dot the vector field with that. Roughly by definition, this is what this kind of notation means. So then, like I said, turning this into a iterated integral is pretty easy, not much to do there. And then let's see, what do we get? Can I do this in my head without writing anything? No, I can't. So 3u squared minus 6uv, evaluated at 1 and 0. That's going to be 3 minus 6v, I think. And then we'll get 3 minus 3. Did we get 0 in the end? Did I do that right? Okay. All right, I guess we got 0. What do you know? It's a pleasant surprise. Okay, so this, so could I break it up into, yeah, that's probably easier actually, or I don't know. Yeah, you could break this up into two, from here on out, you can do whatever you want, however is easiest to evaluate. But maybe this is an opportunity to just bring up something that came up when we were talking about, when we were first talking about conservative vector fields, and maybe it sounds trivial at this point, but it's worth repeating. If you think about like an hour ago when we started this one example, the first thing that we thought of doing is checking to see if the vector field was conservative, right? And we said that if it's conservative, this is a closed loop, so I know that we'll get 0. Well, it turns out we got 0, right? Does that mean that the vector field's conservative? No, it's just a coincidence. We just happened to get 0, right? You are allowed to get a closed integral which is 0 over a non-conservative vector field. This vector field is definitively not conservative because the curl is not 0. We just coincidentally happened to get 0 at the end. What do you know? Yeah, so you have 72 hours. If you do a problem per hour, you could do 72 problems. So, and that's definitely what you should do. None of you should sleep at all over the next 3 days. You should pull 3 all-nighters in a row and do nothing but math and get really stressed out and remove like 3 years of your life. That's the move for sure. Okay, so am I having office hours during the exam? Right now, no. I know that Noah is, but I don't feel comfortable doing that at this point. Maybe he would let me, but since it's a final exam, I don't want to have to walk that line. Noah can do it because he's the head honcho, right? But right now, I don't feel comfortable doing that. We'll see, but don't get your hopes up. It's not that I don't want to help, obviously. Hopefully I can be helpful now and tomorrow and stuff like that. But right now I'm not planning on office hours during the exam. So tonight and tomorrow, that'll be it for the year, which is crazy. Yeah, so I got asked privately if Noah's set his office hours yet. I don't know. Finals should get released around midnight, Saturday, tomorrow night. Yeah. Anyway, that's fun. Any questions about this one? That was a pretty involved example, I think. So at this rate, maybe we'll just do 2 examples, the entire midterm review or entire review session. I want to do this one next. This one's kind of fun. And probably slightly different than anything you guys have seen yet, maybe not. So I'll let you look at it while I read it out loud. In this next example, we have a vector field, x over x squared plus y squared plus z squared, y over blah, 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 z over blah, blah, blah. Oh, damn it. Let me think. Okay, well, give me a sec. Okay, let's do this as written, and then I might change it depending on what happens, because I should have thought about this harder. So here's the question. There's a vector field. It's defined on R3 minus the origin. And the question, all I want to know is, does this vector field have a vector potential? In other words, can we find a vector field G such that the curl of G is F? Okay, and so, yeah, you guys have a good idea, which is one way we could test this is by taking the divergence. Oh, the coordinate where it isn't defined is the origin, 0, 0, 0. Hopefully that is clear from looking at it. So let's take the divergence. Why, maybe before we do that, just to remind you of the point. We know that if you take the divergence of the curl of some vector field, what do you get? You get 0. Okay, so yeah, star is a good point. And this is ultimately going to be what we get at, but we might have to do something different. I'm actually not sure. I'm not sure how this is going to work out. The idea behind taking the divergence is if we get something which isn't 0, then we win, and we can definitely say that there's no vector potential. But Dar is correct in that if we get 0, I don't know. We can't say anything because, like what's being pointed out is, in order to conclude the existence of a vector potential with the divergence being 0, the vector field needs to be defined on all of R3. And this vector field's not. So we'll cross that bridge if we need to. Yeah, and after this, I'll bring up the potential stuff. So the point here is that if the divergence is not 0, this implies that there's no vector potential. But if the divergence is 0, then we'll have to do something else. Okay, so Aman thinks it's not going to be 0, which means I'm going to have to change the problem after we do this. But so, because I want it to be 0. But that's okay. I'll man up and we'll do the easier version of the problem. So note that the divergence of f is, all right, so what do we have to do? We have to compute the x derivative of this. So this is going to be a little annoying. Low d high minus high d low square the bottom and off we go. Which is going to give us, well, I'll simplify later. And then by symmetry, you know, all the others are exactly the same. But with the other variables here. Right? So we would get common denominator of x squared plus y squared plus z squared squared. And then on top, we would have here negative x squared plus y squared plus z squared plus x squared minus y squared plus z squared. And then plus x squared plus y squared minus z squared. And is this 0? Damn it, I guess not. Because we're left with so these cancel out, these cancel out, and these cancel out. And so we get x squared plus y squared plus z squared on top. Okay, and that is definitively not 0. So since the divergence is not 0, by this blurb, there is no vector potential. Done. Okay, I'm gonna let you think about that. First example took us 50 minutes. Second example took us 5 minutes. So, you know, it's a decent pace on average now. And while you think, I'm gonna see if I want to change this slightly. Maybe some of you can already see what I'm getting at. So, okay. So I gotta, okay, thank you. So someone privately, I think, is telling me how I should change the example, which tells me that person, I think, maybe knows what's going on. So before I do that, though, I was going to try to do it in my head, but then I'd probably embarrass myself. So thank you. We'll do that next. Okay, so some questions. What if you take the limit as the variables go to the infinity? Don't you get 0 there? You do, but in order for, so when we say like divergence being 0, I mean everywhere, right? So it's got to be 0 everywhere. And so if you can find one point where it's not 0, done. And then, okay, private question, which is exactly the point of what I'm about to do next, is if the divergence is 0, does that mean there is a vector potential? Or no, since it's not defined on all of R3? And that's exactly the point. So here's what we're going to do. We're going to do another version of this problem, which will be a little more interesting. Because that's exactly what I want to talk about. And so the private suggestion I got was to put a 3/2 here, and a 3/2 here and here. For some reason, that shouldn't change anything. So it's something a little more complicated. Let's see if we can figure this out. Or does that change it? But I'm just multiplying the whole vector field by 3/2, and differentiation is linear, right? So at the end of the day, we would just get 3/2 times, where did that go? Won't we just get 3/2 times that? Maybe I'm losing my mind. Okay, let's try. I very well might be losing my mind. So as usual, I should work these things out ahead of time. So really quickly, if I take a derivative of this first component, I'll get low d high minus high d low is 3x squared. So from this term, I would get a 3/2 minus 3 is negative 3/2 x squared. Yeah, it's something a little more complicated. So all right, well, we'll come back to that. Let's do something else. Also, it's getting really hot in here. You probably have to adjust the power of the denominator. So I'm going to figure out how to do that later, maybe for tomorrow, because this is interesting and this is what I want to talk about. So put a hold on that, come back to it. Let's do something else instead next. Do you want a fun one or a not fun one? So I got a private question, which was, could you say that there's not a vector potential no matter what, since f is not defined at the origin? So what I'd be looking for is I'd be looking for a vector field defined on everywhere except the origin. All of my questions are fun. I don't know about that. So there were 2 votes for fun and then 1 vote for easy. So I guess let's do a fun one and then we'll do an easy one after that. This counts as fun to me. And if you watched Noah's lecture today, then this kind of thing should feel familiar, but slightly different. Damn it. I'm pissed off about, this is going to bother me now. It's probably, okay, really quickly, 60-second break. We need a break. Just let me try one more thing. I think is it, do I want this? And I'll worry about it later. This is what tomorrow's for. Well, we need to save something good for tomorrow. Oh, right, this was my fun one. Okay, so let's read this. Let C be the circle parameterized by this thing. So R1 of t is cosine, sine, and then 1 from 0 to 2 pi. And then let D be the circle parameterized by cosine t, sine t, 0. And the question is, f is a vector field defined everywhere. And I'm telling you that the curl of f is that thing, 0, 0, z squared. I'm also telling you what the integral of f over d is. It's 5. And the question is, what does this mean about the integral over c? Okay. Also, Noah said this in class today, and this is slightly different than what he did, but he said, he made it sound like there would be a question with this kind of flavor, at least. Like I said, this is going to be slightly different, but the kind of concepts that Noah was talking about today could be important. Okay, so let me draw some pictures and I'll let you guys think. This has got to be in the book. This is really going to bother me until I figure it out. If I didn't have a bunch of people watching me right now, then I could probably do it in my head, or not do it in my head. I could figure it out, but I have not seen the final. No. So D. No, that's a good question. These are supposed to be R's, and I think they're just ugly R's. Sorry, R. Thanks. But okay, so there's various ways you could get 0 divergence, but I very specifically want, I want a positive multiple of x, y, and z up here. Yeah, and I have a reason for that too. But there are definitely ways you could get 0 divergence otherwise. Okay, forget about it, Joseph. Do it tomorrow. There's C. No, that was D, I guess. And I'm synthesizing some information here. So what I just drew is D. It's cosine sine 0, so this is definitely a counterclockwise circle in the xy plane. And then the other circle, C, is the same thing, just moved up to a height 1, right? So not very accurate to scale, but what are you going to do about it? What we want to do, we know that the integral over D is 5, and we want to figure out the integral over C. Alex has a great idea. We're eventually going to make a cylinder, and I'll tell you why. But before I do that, the first thing I want to say is what we cannot do is evaluate it directly, right? Because we don't know what the vector field is. So because we don't know what the vector field is, we're going to have to do something clever. And Alex is getting at the clever thing, which is, well, the only piece of information that we know is the integral over D. So somehow we would have to relate this integral to this integral. That's really our only hope at getting anywhere, right? And how in the world could we do that? You know, maybe you don't see exactly where this is going yet, but if we're going to relate something of C to D, maybe we want to think about introducing a cylinder. And this isn't going to really look like a cylinder. But let me draw a cylinder here. So I'll let S be, yeah, and so I think Katie has the right idea too. Let S be the cylinder. So what cylinder would I want specifically? Yes, x squared plus y squared equals 1, because these are both circles with radius 1, so that cylinder would connect them. And since this one's sitting at height 1 and this one's sitting at height 0, I would probably let the z coordinate range from 0 to 1. Oh, thanks. Yes. Okay. Now, okay, so I think privately someone told me that the thing that I scribbled out earlier, the power of 3/2 would work. Thanks. We'll come back to that then. Because that was the one I was most excited for. I'm kind of sad. Okay, and then Dara says orientation. That's good, because ultimately what we're going to do, I haven't mentioned this yet, but if we're, or I think actually, so Katie said something about flux. What we're going to do is use Stokes Theorem. Stokes Theorem is going to be the thing that relates these two. And to use Stokes Theorem, you know, we have to compute flux, which means we need an oriented surface. So we need to give this cylinder an orientation. We'll finish this one, we'll do an easy one, and then maybe we'll come back to that other one. Oriented, so what do you guys want? In or out? Doesn't matter, we could do either. But we gotta pick one of them. Okay, outward wins. That means that if I draw a normal vector somewhere, or a normal oval, something like that. Okay, so I got a good private question, which came up earlier when we were doing the first problem, which is, does the orientation of the surface have to match the boundaries? And the answer is no, in the sense that that's actually going to be impossible here, if I understand what you mean. you will not be able to write down a surface which has C plus D as a boundary. So you could orient it however you want. You just have to take into account the boundary orientation correctly. So the deal with all this orientation stuff is that a lot of times you can do whatever you want. The only thing that you have to do is make sure that things line up correctly. I think you'll see what I mean. That's a good question. And then another private question was, given a surface like this, is it hollow? Yeah, so when I say the cylinder, I'm thinking about a toilet paper roll, if that makes sense. That's what this cuts out. It's just the shell of the cylinder without like a top or bottom or anything. Okay, so getting to the, sure, it can be charming. So getting to the private question, the next thing to think about if we're going to use Stokes' theorem is what is the boundary of S? I asked that question in the first problem we did, and I'm asking it again. So let's think about this in two pieces. Or do you guys say D minus C? That sounds good. Let's go through that carefully, just for everyone. So we need to think about the top boundary curve. So if I drew a normal vector really close to the top like that, stick my thumb in the direction, stick my right thumb in the direction of that normal vector and curl my fingers, that curling motion is going to go this way. So if we take the boundary orientation of this top curve would be going this way. And that's going the opposite direction that C is going in. So this is where the negative C is coming from. And then if we do the same thing down here, stick my thumb in the direction, curl my fingers, that curling motion goes like this, which is going to push this curve this way. And that agrees with what D is, right? So you guys got it. What that tells us is that the boundary of S is D minus C. So again, to address that previous question is like, does it have to agree with the boundary? Not necessarily. We just need to make sure that the thing that we write down matches up in terms of the names that we already have. Also, I'll go past 8 again, probably. Maybe like 8:30 or 9 tonight. In case you were super worried about only getting to do 40 more minutes of math. Because I know you all just had so much fun doing multivariable calculus on Friday night. Okay, so what would Stokes' theorem tell us? So by Stokes' theorem, well, what does Stokes' theorem say? It says that the integral over S of the curl of F, which by the way, we know what that is, so that's good. This is the integral over the boundary curve of F. Yeah, my R's, why is that happening? What am I writing that makes... Okay, now I'm losing my own mind about my own terrible handwriting. One of these days, and some of you guys watching can back me up on this, but some of you guys that just met me this quarter, probably the whole quarter, you're sitting there thinking, why is this like 25-year-old grad student, why does he write like a kindergartner? And I promise that if you ever see me on a chalkboard, it's better. You guys got the short end of the stick this quarter with my on paper handwriting, which is much worse. Okay, so let's figure out what we have here. We're told that the curl is 0, 0, z squared. And then the other thing I'm going to do here is, since the boundary is d minus c, we can split this line integral up into two. Boundary over d, sorry, the integral over d minus the integral over c. Only 25. That sounds old to me, though. I feel like next year, yeah, like in a couple of years, I'm going to be able to say I'm almost 30. And that's weird. I don't like that at all. And I'm still in school, so how about that? Now, we know that what do we know? We know that the integral over d is 5. So that's one piece of the puzzle. The other thing that we have to figure out is this. And this is a surface integral, right? So we know what the surface is. We know what the vector field is. We can just evaluate this. So what do we need? We need a parameterization. So maybe I'll do this over, excuse me, I'll do this over here in red. What do you guys think? What should my parameterization be? Cosine of u, sine of u, and then v. Thank you. And I probably send u from 0 to 2 pi because u is acting like my angular coordinate here. And v I would send from 0 to 1 because that's what the cylinder ranges from. And then we need to make sure the orientation is correct because I want this to point outwards. So I'll compute the normal vector. This is going to be the u derivative is negative sine of u, cosine of u, 0. And then the v derivative is 0, 0, 1. So what do we get? We'll get cosine of u, sine of u, and 0. And the question is this outward? And probably all of you can tell me because you probably did the same computation for your homework that was due today or that's due tonight or something like that. But I would say this is outward. For example, we could compute this vector when u and v are both 0. So if u and v are 0, what point are we at? We're at the point 1, 0, 0 using this. And then what is this vector? It's the vector 1, 0, 0. And so that looks like this. And that does point outward. So outward does not necessarily mean positive in the y direction. Outward means outward, and there's sort of no getting around the geometric intuition there. Exactly, so it depends on where you are. So the idea here is that if I walked up to you on the street and I said, is this vector outward or inward? And that was the only information I gave you. That makes that, I don't know, like it completely depends, right? You would probably run away. I'm pretty fast though, so I would catch up to you and I would ask you again. Is this outward or inward? And you would tell me, I need more information. I need to know where on the surface I am. Okay, so that's a good question. Do you have to pick a point like on the boundary? No, nope, you could pick a point anywhere. That just happened to be the point I picked, yeah. Okay, Jessica, this is a great question. Does upward always mean positive in the z direction? Yes, it does. So upward is a globally well-defined notion. That's a great question, and that's sort of potentially unfortunate. Something like upward or downwards, that makes sense globally. That means like positive z or negative z, but outward or inward depends on the surface. Cool. Okay, so this is oriented correctly, so let me convert this. 0 to 2 pi, 0 to 1, and then I'm going to take 0, 0, z, oh. So when I change the vector field, z squared, oh, sorry, is v squared. I got excited too early, but I think now I'll get excited. The normal vector is cosine of u, sine of u, 0. dv du, Jesus. That's pretty nice. The dot product is 0. Which means this integral is actually 0. Sorry for the haphazard circular equations. Maybe don't do that on your test. I'm setting a bad example. So again, I just evaluating a surface integral. I didn't do anything fancy there. I just parameterized, computed the normal vector, blah, 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 blah. And what have we shown? We've shown that this equals 0. So we're done, right? What does this mean? Well, let me record this. So 5 minus the integral over f equals 0. So the integral over c, which is what we cared about, it's got to be 5. Done. Cool. Any questions about that one? Yeah, so I got a good private question, which was, I'll zoom out. So if the curl was 0, so if the curl was 0, a couple different things would have had to happen. So I got a couple private questions. Maybe I'll do the second one first. So one of the questions was, why couldn't we just connect this with 2 lines? And the other question was about this curve arithmetic thing. So I mentioned today that like, oh, this is like Noah's example or whatever. And if you think about what Noah did today, he did the kind of curve arithmetic stuff where you connect things with 2 lines and go from there. I got another question. I'll think about that in a sec. So let me talk about the curve arithmetic stuff. The reason why we couldn't do curve arithmetic here is because usually when we do curve arithmetic stuff like that, it relies on the vector field being conservative on simply connected domains. Usually the point there is that we do curve arithmetic when the curl is 0. So if you think about Noah's example from today, he told you, oh, and then Dara asked the same question privately. Yeah, so a number of questions about the same thing. If the curl was 0, you could do curve arithmetic stuff. We couldn't really do that here because the curl isn't 0. Because usually when you do curve arithmetic, you say like, oh, this loop is in a simply connected domain, the curl is 0, so therefore the integral is 0. So the reason why we couldn't do that is because the curl wasn't 0. And so another question was, couldn't we have known this after we found the cylinder due to surface independence? Not quite. So surface independence is something different. Surface independence would be saying something about how the flux through this cylinder is like the same as the flux through some other surface with the same boundary. For example, this like hourglass shape that you guys had in the homework. And that's not quite what we're doing here. The thing that we're interested in is over the curves. So not quite with surface independence. And I do want to say one thing about surface independence and path independence. But first, I got another question was, could I go over how I parameterize the surface again? Yeah, so I didn't do that. I kind of blazed through that. So the surface is a cylinder. Here's how I would think about it. The surface is a cylinder, and it has equation x squared plus y squared equals 1. So if you took this cylinder and kind of just smashed it down onto the xy plane, what would you get? You would get the unit circle, right? And how could we parameterize the unit circle in the xy plane? It's something like cosine u sine u. But we don't just have a circle in the xy plane, right? It kind of varies up and down between 0 and 1. So that's where this component comes in. This parameter accounts for the height of the cylinder. So you can think about this as describing like circles, and then this is moving up and down. Yes, and so I think Katie's pointing out what I'm about to describe, and maybe let me make a new page for this. And then, yeah, so for surface independence, you could have a sum of multiple surfaces. That's totally fine. Yeah. But here's something I want to say about path independence. And then I'll say the same thing about surface independence. And if this is confusing, don't worry about it too much, but hopefully this makes some sense to some of you guys. Path independence is a weaker form of Green's theorem, or Stokes theorem, let me say that. So here we have path independence, which you can only use if the vector field's conservative. On the other hand, we have Stokes theorem. Didn't like what I was about to say, I guess. Stokes theorem or Green's theorem you can always use this. And path independence is like subsumed by Stokes and Green's theorem. So in some sense, path independence is like, oh, it's a weaker version of an argument that you can always do with Stokes or Green's theorem. So if that doesn't make sense, don't worry about it. If it does make sense, great. And the point is, if you want, you never have to do path independence ever again. Or maybe let me say it this way. If you want, you never have to use curve arithmetic ever again, I claim. Now that you know Stokes' theorem. Just use Stokes or Green's. And again, so for those of you guys that were in discussion section, was it last Thursday? I did one of those curve arithmetic examples where I drew some stupid picture like this that we could have done with curve arithmetic. And what did we do instead? We used Green's theorem, right? And it was a lot easier. And I claim that now that you know Green's theorem and Stokes' theorem, you never have to do path independence ever again if you don't want to. You could use it if you want to, but you don't have to. Stokes and Green's theorem are strictly stronger statements, and they subsume path independence. So the only reason we ever had to learn, they subsume curve arithmetic. So the only reason we had to learn this curve arithmetic stuff, like you did on the second midterm and the second homework, was because we didn't know Green's or Stokes' theorem at the time. And the same thing is true about surface independence. Again, if this sounds confusing, don't worry about it, but I claim that you will never have to make a surface independence argument ever again if you don't want to. Because now you know the divergence theorem. And we can do an example like this later, sometime tonight or tomorrow if you want. But surface independence is a strictly weaker form of the divergence theorem. And any argument using surface independence is completely subsumed by the divergence theorem. So just use the divergence theorem. Anyway, like I said, if that's confusing, don't worry about it. I wasn't, but that's a great idea. Maybe I'll do that over the summer at some point. I have some plans to redo the early bad videos. And yeah, that'd be a good video to make. So like I said, don't worry about this if it doesn't make sense. If it does make sense, then hopefully that means you really understand what's going on. And that's a good sign. But if it doesn't, don't worry about it. I'm ranting about philosophy of whatever. Anyway, let's do an easy question. We'll do an easy question and maybe I'll go back to that vector field one with the divergence. Then I'll see how I'm feeling after that. Let's do this. Okay. I think almost literally every question we've done tonight has been evaluate this line integral. So anyway, in this question, I think should be pretty quick. C is given by this equation for x between 1 and e, oriented from left to right. So I don't know exactly what this looks like, but let me just draw a quick picture. There's 1, there's e, and so the curve is definitely decreasing, so it probably looks like this. We've got a vector field, and as usual, all we want to do is evaluate the line integral. What do you think? You know, just to throw out ideas out there, we could do it directly. But why would Joe not want to do it directly? You could try. Yeah, I didn't actually try myself. Yeah, because he probably thinks there's an easier way. But if you look at this, so Ricardo's pointing out, I think, how you could parameterize. Like you could call xt and then y would have to be this. And then if you think about that, like setting up the line integral, I have no clue how you're going to deal with that in terms of integrating. So perhaps there's an easier way. Okay, so I think you guys are pointing out, if this is conservative, we could maybe use path independence. Sorry. I should have written curve arithmetic here. What I wrote is true, but path independence is healthy to think about. Curve arithmetic is the thing that you don't really ever have to do if you don't want to. So we could do that. But yeah, we could do that. We could use Green's theorem. That would effectively give us path independence pretty much. And so you could definitely use a straight line. You could show that the curl is 0. You could use a straight line and it's probably not so bad. Does anyone think there's an easier solution? Or just for the sake of thinking about all of our different techniques, would there be anything else you could do? So we could absolutely do the path independence thing and use a straight line. Yeah, I mean, so you guys have pointed out that it's conservative. What if we found a potential function? If we found a potential function, then we could just plug in the endpoints and we don't have to do any like line integration at all. This is what I would do. Mostly because when I look at the vector field, it's simple enough that I could almost eyeball a potential function. So this is scratch work here. So let me show you what my solution would be. But again, you could do this in a number of different ways. Yeah, I think Dara's got it. We could get this by saying, like, you know, if I integrated this with respect to x, I would get x cubed plus xy squared plus something. And then if I integrate this with respect to y, we would get xy squared plus, if need be, something. So what if I just take this? That would satisfy it. So in my actual solution, I could say, this is what I would say. I would do this in my head or on scratch paper or whatever. And I would just say, let f of x, y be x cubed plus xy squared. How did I get that, you may ask? I'm not going to tell you. Who cares? All I'm going to do is prove to you that it's a potential function. That's all I need to do in my solution. As long as I show that it's a potential function, you know, maybe this came to me in a dream. I don't have to tell you how I cooked it up. I just need to prove to you that it is in fact a potential function. So note that the gradient of f is what? Well, it's going to be 3x squared plus y squared, and then 2xy. And that's f. Okay. And the vector field and the functions defined everywhere, so therefore, f is a potential function for f everywhere. Yeah, so I don't know, I feel like I should make this explicit, but anytime I write a thought bubble, the reason why thought bubbles are thought bubbles is because they're in my head. So anytime I do like an example solution like this, I'm sort of pretending most of the time that if I were taking a test or if I were doing homework, this is what I would write. And the things that are not in thought bubbles, that's what I'd be writing. Usually anything that I put in a thought bubble isn't necessary. It's not something that I'm actually writing on the page. Thought bubbles are up in here. So like I said, I wouldn't actually show any of this. You wouldn't need to. Even you could if you wanted to, but you wouldn't need to show any of this scratch work. The only thing you would need to do is just pull this out of somewhere and demonstrate, demonstrate that it is in fact a potential function. Therefore, we can use the fundamental theorem of conservative vector fields. Maybe before we do that, let's figure out what the endpoints are. So this endpoint is, well, the x coordinate is 1. And then what would the y coordinate be? It would be 1 over e plus log of 1 is 0, so 1 over e. And this one would be e comma 1 over e to the e plus log of e is 1. So by the fundamental theorem of conservative vector fields, this integral that we care about, just to reiterate, like this is the integral of the gradient, and the fundamental theorem says that to evaluate the endpoint, yeah, they're not great endpoints, but that's okay. We just take the potential function evaluated at our finishing point, minus the potential function evaluated at our starting point. And little f is x cubed plus xy squared. So this one right here would be e cubed plus e times 1 over e to the e plus 1 squared. Lovely. Minus, bet I can fit that up here. F of 1 comma 1 over e would be 1 cubed plus 1 times y squared is 1 over e squared. Done. So that's what my solution would be. Again, you could do this in other ways. Perfectly valid solution would be to take the curl, say this is defined on a simply connected domain, so therefore the vector field is conservative, so therefore I can use path independence, and then you could pick a straight line and then evaluate the line integral over that, and then you should get the same answer. So in the first, yeah, e to the e, it does kind of look like a 2. So you could definitely do that. But if you get lucky enough, like if you can find, if the vector field's simple enough that you can like eyeball a potential function or something, then, you know, that's arguably even easier because you can just add two numbers together. Yeah, so Katie's pointing out something good or bad or something, at least, is that if you think about all of the techniques that we've had, that we've developed now, there's a lot of different ways to approach one question. And this is why pretty much every example I do, this is why this is so important to me. What do I always say? I say, you know, in discussion, like, I just spent 10 minutes talking about the divergence theorem, so I bet we're going to use the divergence theorem. But, you know, when you get all these random problems that came from who knows where, from the depths of my brain, and like 90% of the problems are compute this line integral, right? What do you do? Yeah, so if you wanted to use Green's theorem, I wouldn't actually do that here. But if you wanted to, what you could do is you could add in like a straight line. And then by Green's theorem, the double integral of the curl, which is 0, would be this minus this. So therefore, this would have to be the same as this. So it would basically, it would immediately give you the same statement as path independence. That's kind of what I was talking about with like path independence being subsumed by Green's theorem. Exactly. Okay. How you guys doing? Okay, some people are tired, some people are not tired. Oh yeah, I should get my snacks. Okay, so here's what we're gonna do. Let me go back to this problem because this is the one that I wanted to do. And then someone told me earlier that the fix is this. So I'm gonna get you started, or I'm gonna say some things, and I'm gonna go grab my snacks, and then I'll be back. Powers need to be 3. So are you saying if I do this? No, I want, okay, so maybe not. I want x squared, y squared, and z squared here. So I'm looking for I'm pretty sure it's gonna be this to some number. This is what I want. Is it 3/2? Yeah, okay. And I want this for a reason. Okay, so here's the deal. So, you know, throw back to this other question that we did. Here's a vector field. It's slightly different than the one that we looked at the first time. It's x over blah, 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 blah to the 3/2, blah, blah, blah to the 3/2. And the same question. Is there a vector potential? Okay, and so the point here, if Elijah is correct, which we'll confirm after I get my snacks, but think about the first example that we did. The divergence wasn't 0, right? If I go back to this, sorry, I don't know where it is. In the version that we did here, the divergence wasn't 0, so boom, no potential. What's going to happen here is that the divergence will be 0. And so this is, this is what some people were asking about earlier, which is, so then what? Does that mean there is a potential function? And the answer is not necessarily, potential vector field, sorry. The answer is not necessarily, because we're only allowed to make that conclusion if it's defined on all of R3. And this is definitely not defined on all of R3. So we don't know. So that's what I want you guys to think about while I get my snacks. The divergence is 0. So we don't know. And the question is, now what? Is there a potential vector field? Why or why not? Okay, brainstorm or take a nap. I'll be back in like a minute. Okay, I'm back. Yes, it's blueberry Greek yogurt. And garlic and onion Triscuits. So my breath is going to smell great. I'll wash it down with my cranberry lime generic brand LaCroix. Okay, dip the Triscuits in the yogurt. Yeah, may as well. Let me try. Probably won't be very good. All right, Anna, you don't have to watch this part. This gets dipped in cottage cheese. I'm into that. Actually, wasn't that bad. I'm very allergic to peanut butter, so that would likely kill me. So no, I've never had one. Probably never will. Yeah. I love pickles, though. Yeah. Did anyone have any revelations for the math problem? If not, I'm gonna give you some mental motivation. This should feel familiar, right? Let me start out being kind of vague, but this is a really cool problem, and I think this is gonna, hopefully this will click with some of you guys. Does this situation feel familiar to anyone? There's a vector field that we've seen a couple times previously. Yes, the vortex vector field. What do we know about the vortex? So forget about this problem for now. Go back a few weeks. Think about when we first learned about the vortex field. What was kind of interesting about that one? Yeah, so it plays nicely with circular stuff, but kind of the interesting thing was the vortex field, it's an example of a vector field which is not conservative, but the curl was 0, right? So think back to when we learned about all this stuff. We learned about how, oh, if the curl is 0 and you're on a simply connected domain, then the vector field's conservative. And the question was, so if the curl's 0, does this mean that the vector field's conservative? And the answer is no. in the example is the vortex vector field, right? The vortex vector field is an example of a vector field where the curl is 0, but it does not have a potential function. So that's old news, something we knew. How did we show that the vortex field is not conservative? What did we do there? You couldn't use the fact that the curl is not 0. Yes, so the way that we showed that the vortex vector field is not conservative, let me write this down. I'll call it H. Is we found a closed curve C such that the integral of that vector field around the curve was not 0. Okay, so I'm making you think now, why does that show that this is not conservative? What was the point there? Right, so basically because it violates the fundamental theorem of conservative vector fields, the point here is that if it was conservative, then the integral over a closed loop would be 0. Okay, so Elijah's got the right idea, I think. So the point here is that we're dealing with a very, very, very similar situation, but we're up a dimension, right? So rather than talking about closed curves, we're going to be talking about surfaces. And that's exactly what we'll do. We'll integrate around a sphere around the origin. But before we do that, I want to think about what is the point? What would that tell us? Noah mentioned this very briefly one day, but what if you apply Stokes Theorem to a surface with no boundary? What would Stokes Theorem tell you? So if S has no boundary, you get 0, right? That statement is the analog of the statement about conservative vector fields over closed loops, giving you 0. It's the same statement. Closed loop doesn't have any boundary, so by the fundamental theorem, you get 0. That's what this says. Stokes' theorem would tell you that if you integrate the curl of something around a vector, around a surface with no boundary, you'll get 0. So what if, so here's our goal. We're going to look for a surface with no boundary. So a closed surface such that the integral, of f of our vector field over that surface is non-zero. This is so cool. This is a complete analog of what we were doing with the vortex vector field down a dimension. If we can do this, if we can find a closed surface where we integrate the vector field and get something not 0, then that tells us that f cannot look like this, right? There cannot be a vector potential because if there was, by Stokes' theorem, we would get 0. So we're doing the exact same thing that we did with the vortex vector field. We're just up a dimension. And rather than using a closed curve and the fundamental theorem of conservative vector fields, we're using a closed surface and we're using Stokes' theorem. But other than that, it's exactly the same concept. It's exactly the same argument. I think that's so cool. And I think if you understood what I just explained, it should click and you should be like, oh, like, yeah, that makes a lot of sense. So let's do it. And Elijah said, so is there any situation where it's preferable to use a 2D loop in place of a sphere? Well, that wouldn't tell us anything here because the point is Stokes theorem. It's exactly this fact. And in this fact, we're doing a surface integral. So we really do have to find a surface. And I think Elijah suggested earlier, like we could pick a sphere. That's maybe not a bad guess because of these things here, excuse me. So let's do that. So let me let S be the unit sphere, oriented outwards. Doesn't really matter, why not? And then I'll say something that, well, I don't know. Never mind. What we want to do is we want to compute the integral of f over s. So what do we do? Let's just compute it. How could I parameterize a sphere? We could use theta and phi and do our spherical coordinate stuff. So x is rho sine phi cosine theta. So we could, rho is 1. So sine phi cosine theta, sine phi sine theta, and then cosine phi. For theta between 0 and 2 pi, phi between 0 and pi. That's the standard parameterization of the unit sphere. It's kind of crazy. So then the normal vector is going to be, I'll try to do this quickly, the theta derivative cross the phi derivative. Oh my God. Which is, what is happening? Sorry, I don't know why it's doing this. Okay, I got a long private question. I'll look at that in a second. Okay, you can trust me that the normal vector here is rho squared sine phi times is it just going to be rho sine phi times xyz? Okay, let me, instead of computing it directly, instead of actually computing it, which we could do, let me just give you a more intuitive argument for why it's not 0. We don't even actually have to do computation. We just have to show that we get something non-zero. But this should be pretty clear based on the geometry of the vector field. So what I'm going to do is I'm going to draw a side view of this sphere. This is sort of the point, and this is what you should be thinking about rather than just like blindly doing computations. So here's the sphere. And again, I'm drawing the picture in 2 dimensions just for the sake of drawing a picture, but I want you to be thinking about what's happening in 3 dimensions, and this is just a 2-dimensional representation of that. And I outwardly oriented it. So there are the normal vectors. Question: what does this vector field look like? Like if I ask you to describe that vector field geometrically or to draw it, yes, it's radial, right? So there's this funny, let me do this. There's this common factor of 1 over blah, 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 right? So I could write F as, I could pull that out. And it's some function, some positive function times x, y, z. And this right here, we know this is a radial vector field. So what does that tell you about the vector field at every point on the sphere? It's pointing out like this, right? Exactly, that's exactly the point. So what I'm about to say is that if I were to ask you, just based on this picture, what would the flux of the vector field be through the surface? You know, without actually doing any computation, you should be able to tell me that it's going to be positive. Because how do we compute flux? We're measuring the vector field against the normal vectors with the dot product. And because the normal vectors to a sphere are radial, and because the vector field is radial, we know that the vector field dot the normal vector is positive everywhere on the surface. So therefore the flux, when you add things up, and again, if we actually computed it, like if you did what I was about to do and parameterize and actually just straight up compute it, you would get a positive number. I'm just too lazy to do that right now, and I don't really care what it is. It's just the fact that we get something non-zero. So we get something positive, and then there we go. This is what shows, so therefore, since the flux is non-zero, by Stokes theorem, there is no vector potential. Done. That's what I wanted to do. So that's what I should have checked more carefully before I wrote the problem. Again, I think this is really cool. Hopefully it makes sense to some of you. And what we're doing, well, okay, let me read some of the questions really quick. So the private question was, I don't really understand the question. I can look at it more closely a little bit later, but I think the spirit of the question is, in this two-dimensional situation with the vortex field, really the problem there was the presence of a hole, right? That was kind of the source of all the issues. That's what allowed us to have this like swirly behavior. And here it seems like the issue is, again, it's sort of the presence of a hole. And that's exactly the point. So what I was going to say is that, and this might sound kind of familiar depending on how many videos you've watched. I said this kind of jokingly at some point, but from a mathematician's viewpoint, all of these things that we've been doing, like this vortex vector field stuff, like this problem that I just did, this is an extremely sophisticated way to say that this domain has a hole at the origin. We just came up with the most insanely mathematically sophisticated way to look at this shape and declare, yes, this has a hole. That's what we've done effectively. And that's what we did with this vortex vector field stuff. From my perspective, the whole point of that was to look at that shape and be able to mathematically declare, yes, R2 minus the origin, it has a hole. So that's what we've done. And it sounds kind of stupid, but, and I'm sorry for ranting about the philosophy of this so much, but you should be asking, like, why the hell did we just learn all this advanced multivariable calculus to look at this and figure out that there's a hole? Like, obviously there's a hole. Just look at it, right? You don't need to do all this calculus to look at this and be like, yeah, it has a hole. Or like R2 minus the origin. Do you need to integrate around the vortex vector field to declare that it has a hole? Like, no. But the point is that in math and in life and in harder things, like, what if I told you I have a 70 million dimensional shape and I want to find the holes? What are you going to do then? Are you just going to look at it? Nope. You can't look at a 70 million dimensional shape. You got to do something else to find the holes. And this is where math comes in. You do this stuff. You do 70 million dimensional calculus to find the holes that you can't see. Okay, anyway, let me look at some of the other questions. Okay, so Dara has a good question about, like, in this case, I think the question is about, like, here the point was that the flux was non-zero, and it's a little different with the vortex vector field because there it was like a tangent to the curve. So it's because in the one-dimensional case, we're measuring the line integral. That's the relevant quantity, which is like about tangencies. Whereas in 2 dimensions, the relevant thing to measure is the flux, which is outward. Okay, so what does it mean for flux to be positive or negative? Anytime we talk about flux through something, we're talking about the vector field moving through the object. So that always boils down to measuring how the vector field compares to the normal vectors. This is the case with both flux through a curve and flux through a surface. So for example, this is a 2-dimensional picture, but it's representing a surface. And the idea was that since the flux is positive, what does that mean? That means that the vector field is kind of moving out through the surface. So can I give an overview of what I just did? I'm having trouble understanding the big picture. I wouldn't worry about it too much. This is a pretty sophisticated question. So if you're kind of like, what? Then I wouldn't worry about it. I'd be pretty surprised if something like this came up. I'm happy to talk more about this because this is what's really cool about everything. But we might move on for the sake of doing some more down-to-earth stuff. So going back to the general case, if the divergence is non-zero, there is no vector potential. That's correct. So that was the first version of the problem we did, and that's the much easier case. So if you do something and the divergence is not zero, boom, done. You don't have to do anything fancy. Yeah. And yeah, so what's the point of proving there's a hole if the question says there's a hole? I don't know if I answered that already, but it's sort of not really the point that this has a hole. Like in this situation, like obviously it has a hole, but the whole point of this theory is that you'll run into situations that you can't visualize and that you don't know what the shape looks like. So you do this kind of analysis to detect holes that you can't see. Yeah. Okay, yeah, sorry, scroll down a little bit. Okay, anyway. We'll do something more down to earth now. But if that made sense to anyone, then that's a victory for me. Because this is really the big picture. And this is what I think is really cool about this stuff. I want to keep talking about this, but I'll stop myself. Okay, what else could we do? That's boring. Oh, is that it? Let's do this one. This will be more flux stuff, maybe in the spirit of what we were talking about. So I have curve. Surprise. All right, see you, man. Let me do one more problem, and then I might call it a night. And then if you, yeah, I can stick around for more questions afterwards, or talk about more math if you want. But for tonight, I'll do one more, and then we can pick it up tomorrow. I don't think this one should take too long either. We have a curve, y equals 1 minus x squared, from -1 to 1, oriented left to right. We have a vector field, and I want to compute the flux of the vector field through the curve. And I want to do that in two different ways. One directly, and then using the flux version of Green's theorem. So before we get going, let me just remind you how to compute flux through a curve directly, and then I'll remind you about the statement of Green's theorem for flux. So the flux through a curve, instead of taking the dot product with the tangent vectors to the curve, this is kind of what Dar was talking about, we take the dot product with the normal vectors, and we do that line integral. Computationally, what this boils down to is with your parameterization, x of t, y of t, you take f dot, instead of r prime, which would be x prime, y prime, you take that vector and turn it 90 degrees to the right and dot with that normal vector. So that vector would be y prime of t, negative x prime of t. And it's very specifically this vector, right? It's not the negative of that one. By convention, it's actually this one. Yeah, I don't know which t you're referring to. It's probably this one. I have no clue what that says. This is how we compute flux directly. So let's do that here. So to compute the flux directly, first of all, we would want to parameterize the curve. That's not so hard. It's the graph of a function, so I could declare x to be t. Yes, thank you. We get 1 minus t squared. Let t range between -1 and 1. So then r prime of t is going to be 1, -2t, which means the normal vector that we want here let's see, it would be the y prime of t, which is -2t, and then negative x prime of t is -1. So the flux is going to be, well, abstractly it'll be this. And then when we use our parameterization, this would turn into the integral from -1 to 1 of f of r of t. So what is f? F is x times y, so this is t 1 minus t squared. And then y squared, that's annoying, is that dot the normal vector. Oh, so we get -2t squared, 1 minus t squared, minus 1 minus t squared, which let me try for like 1 second to simplify this, just to see if it turns out nice. I don't actually know. -2t squared minus 1 plus t squared. So 1 minus t squared, and then something like that. I don't know, you could do it. I don't really feel like it. So let's say you get smiley face at the end. It's, 31a at that point. Okay, so we got smiley face. Good job. That's how we would compute flux directly. Again, the only difference there between evaluating a line integral directly is that rather than dotting with r prime, you dot with this specific to the right normal vector. The other way that we can compute flux through a curve is using Green's theorem, right? There's a flux version of Green's theorem. So I'll remind you what that says. So the flux version of Green's theorem so instead of the double integral of the curl over a two-dimensional region, we have the double integral over the divergence. And what does this give you? Instead of giving you the line integral around the boundary, it gives you the flux. And that's it. So if we want to compute this, then, or something like that, we can use Green's theorem by instead turning it into some kind of double integral. Now, let me draw a picture because there's a small subtlety. which is that this curve this is not the boundary of some region, right? It's not a closed curve. So I can't yet apply Green's theorem literally. So what would I have to do if I wanted to use the Flux theorem? Yeah, we could connect the dots pretty much. We could introduce a closed loop by adding in, for example, this straight line D. And then I don't know, which way do you want to orient it? Left or right? Doesn't really matter. We could do either. Okay, let's go right. So let D be the curve in the picture. Oh, I probably shouldn't call it D. Let me call it B. I don't think I've ever called a curve B before. I'll spice things up. This is how you keep things exciting in there. So let B be the curve in the picture. Yes, and that's exactly correct. And so what we'd want to do is, the next thing I want to do is I want to make my region explicit. I'll call that D. So let D be the region pictured. Then, as Dara points out, the boundary of D, here's where we need to think about the boundary orientation in Green's theorem. When we talk about the boundary, we want the region to be to our left, right? So if I think about the boundary orientation here, I'm going this way. So that would be follow B in the correct direction, and then D in the wrong direction. So that's C in the wrong direction. So the boundary of D is B minus C. So we can apply Green's theorem. So by the flux version, which by the way is just the divergence theorem in 2 dimensions. I don't know if that's clear, but think about what the divergence theorem says. It says that the triple integral over the inside of the divergence gives you the flux through the boundary surface. That's exactly what this is saying, down a dimension. Anyway, it's kind of cool. So anyway, by the flux version of Green's theorem, which is just the 2-dimensional divergence theorem, the double integral of D over D of the divergence of F, this is going to be the integral, it's going to be the flux over the boundary of D. Well, we could compute the divergence. I forget what the vector field is. Let me copy it down. So the divergence, let's see, the x derivative of the first component is y, and then the y derivative is 2y of the second component. And then, we've done this kind of thing before. I want to split this up into 2 integrals, which would be the flux across B ds minus the flux across C. this is what we want. So we just need to compute this, and then that'll tell us. So what would this be? This would be, if I set this up as an iterated integral, we're pros at this now, we could go from -1 to 1 dy dx of 3y, and then 0 to 1 minus x squared. And here's my next question. What is this going to be? I bet you can tell me without doing any computation. Yeah, it's going to be 0. Why do you say that? Because that's always the answer when I say, what do we get here? Without any computation. Yeah. What does the vector field look like along the x-axis? So even more than that, that would do it too. But on the x-axis, when y is 0, the vector field's actually just the 0 vector field. So this is 0. So I'm being sloppy here because I'm kind of tired. But this is 0 on the x-axis, so this is just straight up equal to 0. That's kind of nice. So what that tells us is that this thing that we care about is going to be negative this. So the flux of f is going to be negative this iterated integral. And then if you evaluate it, wow, look at that, you get smiley face, which is the same thing we got up here. So everything checks out. Okay, that's flux through a curve in a couple different ways. I would maybe know how to compute flux directly. Probably not a bad idea to know the flux version of Green's theorem. I think both of these came up on some of the practice midterms or practice finals. And then probably a decent intuitive understanding of like what you're computing visually. That's probably good for flux through a curve. Okay. Yeah, so the flux is 0 because, so on this curve B, the vector field is the 0 vector field. So like if I drew the vector field at every point on B, I would just be drawing the 0 vector at every point. And that's because the x-axis is given by the equation y equals 0. So if the vector field is just 0 along that curve, then you're going to be integrating, yeah, you'll be integrating 0. Okay. Let me officially stop there. We'll end part 1 here. Like I said, if you have some questions, I can hang around for a little bit. But that's enough for tonight, I think. And then, if you care, I'll pick it back up tomorrow at 1, I think. Is that what I said? So, until then. Yeah, so if there were questions that I didn't ever answer in the chat earlier that I forgot about. So for the last example, how did finding that the flux is non-zero? Yeah, I'll go back and explain that. So why is it 0 one more time? So this integral is 0 because, so when we do this integral, I only care about the vector field f along B, right? Like if we were to actually do this, we would parameterize the curve and plug it into f, and the only points I would care about f are along B. But B is the x-axis, and this vector on the x-axis is 0. So like the actual vector field when you plugged in your parameterization is you would just get the 0 vector field. So your integrand is going to be 0 here. Yeah. That's why. Okay, so I'll go back and talk about this nonsense again. And I'll summarize, I think. I talked about a lot of stuff here. So the point was this guy right here. So you may or may not remember this, but I think maybe the day that Noah talked about Stokes Theorem, maybe let's think about what Stokes Theorem says in general. Stokes Theorem says that, you know, this is just a statement that if you integrate the curl of a vector field across a surface, what does this give you? It gives you the line integral over the boundary of the vector field. So that's just what Stokes Theorem says. And so kind of the special case is right here. And this is the important case for us. What if that surface you're integrating over doesn't have a boundary? For example, like a sphere. Like the boundary of a sphere is the empty set, right? It doesn't have a boundary. Well, if there's no boundary, then this integral is going to be 0, right? Because you don't have anything to integrate over. So the corollary is that if you integrate the curl of something over a surface that doesn't have a boundary, Stokes' theorem tells you that you're going to get 0. That part's fine. So let's keep that in mind and think about what we showed. What we did implicitly, I didn't actually do it, but we found a surface with no boundary and we integrated f over that surface. And I argued that we would not get 0. We'd get some positive number. So let's think about what that means in the context of this guy up here. This integral is non-zero. So could this look like this? No, because if it looked like the curl of some vector field, then by this fact we should get 0. But we did not get 0. So therefore, f cannot look like the curl of a vector field. Yeah. Therefore, there's no vector potential. That's the argument. So we could do the same. Yeah, so I feel a little bit bad. I think the presentation of this problem was a little convoluted because I wanted to kind of lead you guys in the right direction. So I talked about all this other random stuff. And the actual point is pretty straightforward. It's like this, and therefore it can't look like it. But if I just pulled that out of nowhere, it would have been like what? And kind of the point is that it is a generalization of this vortex vector field. So I think the organic process of getting there made this seem a little more complicated than it actually is. But yeah, I mean, I think it's really cool. And we could do the same thing in 4 dimensions. We could do the same thing in 5 dimensions. We could find different sizes of holes. It gets more complicated there, but this is like a so Noah kind of talked about this one day in lecture, but this hole here if you asked a mathematician, what is the dimension of that hole? They would probably, or I would tell you at least, and probably most mathematicians would tell you that it's a two-dimensional hole. Yeah. And in the vortex vector field, or like if I gave you R2 minus the origin, and you asked me what's the dimension of that hole, I would tell you that it's a one-dimensional hole. And it's kind of imprecise language. But the point is that in order to witness this hole, what did we have to find? We had to find a surface, right? And a surface is a two-dimensional object. That's pretty much the point. So it's maybe less that the dimension of the hole is 2, but it's that we had to find a two-dimensional thing to witness the hole. Yeah, not necessarily. So it's really the fact that, like, in order to locate this hole, I had to find a surface, and a surface is a two-dimensional thing. Yeah. But in general, like, the purpose of this theory is that given a shape or given an object in math, you can look for holes of different dimensions. And there's kind of like zero-dimensional holes, there's like one-dimensional holes, two-dimensional holes, three-dimensional holes, etc. And so what we found here is what I would call a two-dimensional hole in some sense. So a hole on a line would be zero-dimensional. Yes, that's correct. Because you would use the zero-dimensional sphere to detect that. Something like a black hole in space be a two-dimensional hole? I guess, I don't know. Does it feel like this? Maybe. So it is possible to have a one-dimensional hole in a three-dimensional region. And you're probably not going to like this, but I'll give you an example. What if I took, this is where it gets kind of silly, but what if I took R3 minus the z-axis? So think about like the hole as being the entire z-axis. I would call that a one-dimensional hole. So I don't know if you like that or not. But the reason I would call it a one-dimensional hole is, and this is pretty much the point of the question on the first practice final, where you had like the vortex vector field in 3 dimensions somehow, but like, what would I have to find to witness this hole? I would look for a closed curve. It wouldn't be like a surface or anything like that. I would find a closed curve that wraps around the axis. And since a curve is a one-dimensional object, this counts as a one-dimensional hole. Yeah, okay, that's another great example. So what if I took R3, so as another example, and I removed the unit circle? in the XY plane. That would be a one-dimensional hole. And what else can I say interesting about this? So the question I could ask is, here is R3, and I removed a one-dimensional hole. But then Dara gave me another example of R3 where I remove a different one-dimensional hole. Are these the same shape? Or are they different? In both of them, I just took out a one-dimensional hole. Yeah, so that's a great question, actually. Like, what do I mean by that? And, I don't know, I'm being vague. Could you squish this shape into this shape? I guess that's what I mean. But that's a good question. That's what you should be asking. We're just talking about vague math at this point. And the answer is no, they're not the same. So not even like a linear transformation, just any kind of smooth, squishy, doesn't even have to be linear. Let's see, so is the dimension of the hole plus the dimension of the removed thing plus 1 the dimension of the domain? Not necessarily, because what if I took, so it's a good thought based on, and there might be a way to make that precise, actually. I bet there is. There almost certainly is. But strictly speaking, what if I took R3 and I removed an entire ball? It's like, what if I removed the unit ball? Then the thing that I removed is like three-dimensional, right? But I would count this as a two-dimensional hole. If that makes sense. So the dimension of the thing that you remove can be kind of flexible. I don't know if that makes sense. But like I said, I think the real answer is that's a really good question, and I think there's probably a way to make that precise. Well, maybe. But yeah, the dimension of the thing that you remove is pretty flexible. Like if you took R3 minus a ball, that would be a two-dimensional hole. If you took R3 minus a disk, so remove like a two-dimensional thing, that would be a two-dimensional hole. If you took R3 minus a line segment, I would call that a two-dimensional hole, etc. So it's really more about the stuff that's left. Yeah. It seems like it's really confusing, but it makes sense. It makes sense on some level. Yeah, so all this stuff that I'm talking about, this is getting into algebraic topology realm, which is like pretty sophisticated, like fourth year type, third or fourth year type math for like pure math majors. So like a calculus student wouldn't ever really kind of get the big picture of what I'm talking about. It takes a little bit more to get there. It's cool though. And it makes a lot of sense once you see the like big picture. There's a lot of pretty deep stuff happening behind the scenes here. You might. All right. See you guys. Thanks for tuning in. Now, I had dinner before this. I had a salad. The Triscuits and the yogurt are my dessert, I guess. So. Oh, I guess I can stop recording. Probably not many people are going to log into YouTube to watch me eat Triscuits.